Welcome. You guys are here for our last session of the day, last session of the conference. Wow. Anyway, using mobile LiDAR data as a database for asset management and facilities management solution at Penn State University. Langan used its mobile LiDAR system to scan Penn State University's main campus to create LiDAR point cloud. All AM/FM features were extracted from the LiDAR data exported into Esri Geo Database. Having the AM/FM data in a central database, each department can now make decisions with the most current data available. Assets are able to be updated in real time through the web and mobile applications, such as Collector and Survey 123. Users are able to view these updates with any experiences in GIS software. Our presenters today, our presenter is Chris Holmes, Mobile Mapping and UAV Project Manager with Langan. Chris is a project manager within Langan's surveying department, specializing in mobile mapping and UAV data acquisition and processing. Welcome.
Thank you, Gretchen. Thank you all. I'm packing the room in today, I see. Last presentation. Let me get right to it. On the agenda for this little session here, I have a brief corporate overview of what Langan does, how long we've been around, and then I'll get right into some details of our mobile LiDAR collection, as well as the extraction of planimetric and topographic, FM features from the mobile LiDAR data. And then I'm going to hand it over to Tony the last few slides. Tony Yates, our GIS supervisor within the Langan group, and he can highlight the incorporation of that data into a Geo Database and the implementation within our GIS tools. Langan we're kind of a one-stop shop. We've been around since 1970. We are a full-service engineering firm. We started out as surveyors. That's kind of our dear to our heart. We have about 100 or 1,000 employees. We're ranked number 60 in the engineering news record of the top 500 design firms, number 7 in New York's ENR listings, number 38 in California listings. So we have 30 offices worldwide. Our flag, corporate flag, flies out of Parsippany, New Jersey. We have, on our surveying side of things, we have about 100 GIS survey mapping staff dedicated to surveying, mapping, high accuracy, engineering grade surveys. We have more than 15 traditional survey crews, but probably never less than 15 survey crews, with 7 terrestrial scanners. What I'm going to talk about today highlights our Leica Pegasus 2 mobile mapping system. We have, like almost everybody else, we've got into the drone world here a couple years ago. My background is photogrammetry, remote sensing from aerial photography. So the drone program is kind of near and dear to my heart. We have 4 DJI drones, usually used to create planimetric and topographic data, ortho photos, a little bit of marketing. But I'm making using photogrammetry and making inch to 50 scale maps with our drone program, accurate to survey grade accuracies. We are an ESRI Silver business partner. We do enterprise GIS design and facilities and asset management. So enough said about Langan. Let's talk about this project. This particular project was mobile LiDAR collection of 60 linear miles of road network, the vehicular road network. This project was kind of interesting because it came to us through the GIS department of Penn State, managed out of their Office of Physical Plant. They had, one of the goals of this project was an ADA compliancy type of review, making sure that their access ramps were of the proper spec, slope analysis of those ADA ramps, built properly, cuts, curb drops and such. But also they saw the value in having this data driving the project and having the data in the can, so to speak. So as the project evolves, they can go back and back office and collect more features as the project evolves. So our goal was to drive in phase one of this project was the 60 linear vehicle miles of roadway, extract the features which we had listed with some priority to ADA ramps, and water drainage features for also a flood analysis type of hydraulic study. We were then going to provide the analysis tools, support of those tools, and provide the image viewer. This system collects 360-degree imagery while we are collecting the mobile LiDAR data. And then we were going to put all this into a Geo Database. Here's the project area. This is 60 miles of vehicle roadway. Phase two of this project is going to lead to mounting our sensor on a golf cart or a UTV side by side and driving all the walkways of this of the campus. This is the Pegasus 2 system. This is a pretty versatile system. Prior to this, I had been exposed to a earlier sensor. The versatility of this equipment comes in the fact that it's its own power supply, divorced of the vehicle, the collection vehicle. It makes it be able to mount it on any type of vehicle. And as I said, it has, in addition to the single ZF laser profiler, it has six cameras arranged around its body in 360-degree view, as well as a top sky camera allowing for under bridge detail, under vegetation type of detail, or full 360-degree detail in tunnels. A really versatile system, although heavy, about 170 pounds. It seems to get heavier every time we lift it up. And in this particular project, we added, the machine is versatile enough that there was also some, accuracy enhancements that could be added. This project, we added an 8th camera facing downward. We call that our Pavement Camera. It can, our scanner not only scans into the alligator cracking of asphalt and such, roadway condition, but it also, provides the imagery for that type of detail of concrete and road analysis. In the middle picture there is a distance measuring interval unit, or a DMI, and then we sometimes add a second GPS antenna, calculate its lever arm to enhance the accuracy of our trajectory when we are in a GPS obscured type of area, like a tunnel or heavy vegetation or urban canyon. After driving those 60 linear miles, the screenshot you're looking at there is actually a colorized point cloud from our imagery. As you see, as I mentioned before, phase two of this project is then going to mount it on a golf cart and drive into the walkways of the campus. The feature extractive, there was emphasis on the ADA ramps for this particular project, but the other goal was, they liked the idea of, as the project evolves and having this data in the can to pull this data out back office later on as different features are required to feed into their GIS, their existing plan and topo data, that it was getting a little long in the tooth. And Penn State also wanted to get into, give mobile LiDAR a try. So there was emphasis on the ADA ramps, as well as the water features, top curb, back of curb, catch basins, road centerline, or the break lines of road centerlines. All this data was extracted using TopoDot. software. As with any modern technology, drone technology or LiDAR technology, what really is coming leaps and bounds the last couple of years is the processing software itself. I will say that although we are a partner of TopoDot, we have tried other software programs, and TopoDot is really doing a good job in a lot of automated feature extraction, although some would say there's truly no automated feature extraction. TopoDot does a pretty good job at it. All these lines are 3D, or what we'll call brake lines of the asphalt roadway. Again, the major impetus on this project was for the ADA ramp. So here's our LiDAR point cloud classified to ground, or fit to ground points, classified to bare earth. These are the brake lines, some automated extraction, but it's a visual process. So what isn't automated, we go in and we visually snap our line work to this point cloud data. The ADA models itself, one of the people when we delivered it said, that's worth it right there. Well, I hope it was. But as I mentioned, the 6 cameras plus the 7th sky-facing camera and the 8th pavement camera, the vector data can be incorporated into our imagery. The imagery is geo-referenced and taken in stereo, so what I'll call vertical photogrammetry can be performed on the imagery, as well as a heads-up type of put the cursor on the feature that you want to collect, be it ground-based or elevated. We generated spherical images from those 6 cameras to get a full 360-degree view, almost seamless. You can see a little bit of shading there. But again, going back to getting as much data in the can as possible and using it for future work, you'll notice this video logging type of arrangement. Our vector lines, our 3D vector lines are draped onto the imagery. You can scroll through the project area, and again, each one's geo-referenced and fit to ground control. So the accuracy of the vector data is probably 2 centimeters horizontally and vertically. The aerial imagery is probably depends on the calibration of the cameras. Pretty sensitive in this thing, but we get about a RMS of probably 5 centimeters on the accuracy of the aerial imagery. But again, the true elevation accuracy and data is getting pulled out of the point cloud. I'm going to turn it over to Tony to discuss then the incorporation into our Geo Database and the ArcGIS environment.
All right, thank you, Chris. So once we have all of this data scanned and into the can and features are extracted, the final end goal was obviously to provide a file geodatabase for Penn State that they could pull into their enterprise GIS system. So what you're looking at here is basically all of those features that were driven and extracted from the 3D point cloud and the imagery, just loaded into ArcMap and classified by the different categories of the features that we found. So we pulled things like ADA ramps and catch basins like we've talked about, and just added those into their different feature categories. Inside of each one of these, there's already some pre-canned information about how it was extracted with 3D X, Y, Z coordinates, along with, you can see in the middle there's an image link. So each one of these has a image from the camera that was already linked to it. So when you click on this, as long as you have access to that directory, or if you put it in your system, you can pull up the photo that contains that asset in it, so that you can actually do some kind of verification on your own just to see what the condition of the asset looks like, or just to see what else is in the surrounding area. It tells you the rough height and width of a lot of the signs that we extract too. That's an automated process through the software. It'll automatically identify what signs look like, so a stop sign, and it'll classify the height and width based on what it finds in the 3D point cloud as well. So just an example there, one of the signs that we clicked on was a one-way street sign. Pulling it up, you can see the image that it's pulled from on the cameras as well. So this is that same type of data just being pulled into Arc Pro, which is the new desktop software from Esri, if anybody's familiar with that. This is a really nice software because you can load in that 3D point cloud and have both a 2D and a 3D view loaded up at the same time. And Leica and Esri, I believe, are working on integrating the camera views as well. That's a custom design software through Leica that they're going to be releasing for Arc Pro at some point. So this is just to show you that once everything is already extracted in there, we loaded this into Penn State's system, and they were able to bring all of this into their base mapping already, showing the curb lines, the pavement lines, their buildings, and all of the features that we had extracted for them. And then like we mentioned in the beginning, you heard Gretchen say that you can now use mobile apps to update these things. While this scanner is great for collecting all of the locational information and some estimates for sizes, there's still obviously a lot of information that you're going to want to know about these assets. That's where these mobile apps can come into play, and you can start to populate the back-end data of, this was an example for a hydrant. We can scan a hydrant and we can pull that hydrant location and sometimes conditions from photos, but we don't know the pressures or any of that kind of stuff. So you can go out with these apps and start to get these measurements and continue to populate your enterprise GIS with these type of tools. On the right there is just using Esri's collector. You can go out and collect any other assets in the area or just fill out some more information about inverts when you pop a manhole. That's not going to get collected with the truck, obviously, because the manhole is closed, so it doesn't see below the ground. So that's where these tools come in to kind of bolster your database for things that don't get picked up by line of sight. And then finally, how to present all this information once we have it collected. This is all just loaded into a custom web app that anyone in the organization can access, or you can host this out to subcontractors or students or the public, depending on what level of information you want them to see. All the information was collected, just loaded into this, and everything in here can be pulled up with the attributes as well if you choose to share that information. So here's an example of clicking on one of the signs. I can just see a little bit of extra information about that sign. The MUTCD codes are in there, so R1-1 is a stop sign. We know that that's what the MUTCD code is if we have to replace the sign. So with that, we'll open up for any questions and make sure you guys get to this tour on time. Questions? Yeah.
So, maybe inappropriate type question, but the Google cars going through our campuses, right? And they have imagery, and if you pay them money, they probably have more current versions than the 10-year-old one that might be there, right? They tend to keep stuff that are highly active, more current. Is there any interface between actually just, rather than rescanning everything, using that imagery and mapping that into our GIS application? Well, you're not going to get or what's missing from their process? Well, the question is, why not take Google Earth Street View type photography and incorporate that into your existing GIS database? What is missing out of the Google Street View imagery is a coordinated photo center for each exposure. It exists for Google. I don't know if they'll sell you that photo center, but even if they do, it isn't to the horizontal and vertical accuracy that this imagery is. Yeah, yes, and the ability to, like the video logging video that I showed you, segmented photos, the ability to click on even if you were to fit that Google view to your vertical and horizontal plane, so to speak, you wouldn't be within 5 centimeters of true horizontal and vertical position. If that is a goal of your back office further processing and feature extraction. So accuracy. And
yeah, exactly. How long did it take you to do this, and how fast was the car?
The faster you go, the less dense the point cloud data is. One of the virtues of mobile LiDAR data, and where it's being used pretty extensively, is now the state departments of transportation are accepting this technology and the accuracy that can be gain from it. What they like about it is they now don't have to put surveyors out in the road to be exposed to the dangers of, there's certain roads that I don't care what speed limit is, the people are going 80 miles an hour. And everybody's on their phone anyway. So I just saw a statistic here about a month ago in a surveyor magazine that the death toll for road survey crews is up 80% or some high number like that. So to answer your question, you can capture a highway at 55 miles an hour. And even that gets in people's way sometimes. We can go faster, but picture the point cloud as a helix or a spring, a big slinky. The faster you go, the wider that point cloud spreads out. So ideally, in this particular case, Penn State, the point cloud data, we killed it. I mean, we were going 15 miles an hour maybe at the fastest. So a very dense point cloud. Out on a highway, if we're doing a 4-lane, even at 55 miles an hour, we're going to get to that 3 centimeter, 2 centimeter vertical accuracy. And hopefully nobody got hurt. So the safety aspect is where departments of transportation are embracing the mobile LiDAR data, as well as the accuracy. To get to field topo, or even aerial photogrammetry, to get to a 2 centimeter accuracy on your surface file, you got to do it right. And mobile LiDAR is the same way. It has to be done right. Yes?
What was the file size for that project?
So that 60 linear miles, we drove it. We were about 2 hours, and we were near a terabyte of data. So it's big data. Our IT department hates us, Well, we worked with them. So it's kind of a pilot area, and we yes, we're in, let's talk about numbers. That would have probably been about $25,000 to $30,000, all in, including the tools, the support to work those tools, and data. Data that they own. We don't lease it to them. We don't. The lease doesn't expire. It's their data.
Did you give them raw data, or did you clean it up?
We gave them both. We classified the data, and in that, we aligned the point clouds, we classified, we controlled it to ground, and we took out the noise. But we also gave them the raw data too, because they'd like to do their GIS. They're pretty bright, and they want to have their hands on all the data. Gretchen.
Do they have a contract with you to be able to keep this current? What's their workflow for?
Not as of yet, but we are hoping that they're going to find the value in this, and it will be a.
So that's on people's radar.
Yes.
About
Yes.
how are they going to make it?
Yes. Any other questions?
Just real quick. So, the cracking, like the asphalt, that was kind of one of the drivers for the project, trying to figure out
Uh-huh.
what these cracks are, potentially do repair work on that.
Yes.
So you said there was a type of automated way that your software could figure out where these cracks.
Yes, but unlike road analyzer software, if you're familiar with road analyzer, DOTs pay other firms to use a very low, like a bumper type of low hanging laser sensor. And we can't get down to that density of information, because like road analyzer software will actually analyze each pebble of the aggregate, and calculate coefficient friction numbers. Our data isn't that high of resolution to do that, but the Topo software can extract and classify those alligator cracks and provide a depth and a width to that crack, but not to DOT road analyzer specs.
software can work against any output, not just this particular devices? And that topo.
Topo dot. It is a dot LAS. It is a lidar point cloud extraction tool that can incorporate any LAS file.
Okay, cool.
Yeah. Yep. A good product. I will say it's a pretty efficient software. Anything else? Thank you, everybody.